Welcome back. Now that we have written our library for the EEPROM programmer, we can finally program the EEPROM for our decoder, the binary to decimal and a hexadecimal decoder. And I'll just explain here quickly how I've done it. And it's kind of simple. The beginning of the program here is some definitions for us to make it easier to select which activities we want to do, which programming tasks. If you want to just to erase the EEPROM, program the digits, or dump the contents of the EEPROM, we can just comment out whatever we don't want to do. And then we come to the digits programming part. The first thing is to remember, set up the EEPROM for writing. So we call the library and say eeprog.setWrite. Alright. And then we come to this bit pattern here. And what does this mean? Well, these are the representations, the way we have wired on the schematics, the EEPROM data pins to the 7-segment display. The 0 to 9 and then also to F digits are represented in hexadecimal by this array of data here. 0 is B7, 1 is 14, 2 is 73. And why is that exactly? Well, I'll show you here on this spreadsheet. The way you've wired is that the I/O outputs from the EEPROM 7 to 0 are connected to this segment here of the 7-segment displays. Segment F, G, A, B, dot, C, D, and E. And so, for example, if you want to program the 0, as I said, we have to light up LEDs A, B, C, D, E, and F. So we write a 1 to these segments, A, B, C, D, E, and F. G and the dot are not lit up, so zeros. And the conversion of this binary byte here, 10110111, is B7. And for 1, we just have to light up B and C, so that's what we have here. B is a 1, C is a 1, and the rest are zeros. And that's for all the digits we want to represent, from 0 to 9, from A to F, and also the minus sign, which is a 40 in hexadecimal. So coming back to our code, then now we know what is the data we have to write to represent the digits on the display. And what we have to do now is to encode the digits into the addresses that we'll be calling from our register. So as I said, from address 0 to 7, we have connected directly to the register, is really the number we have to decode. From address A8 and A9, we have the select coming from the counter, the counter that will do the multiplex display. It counts from 0 to 3, and then we have a selector that grounds the cathode of each one of the 4 display digits. So as it happens, the way I've wired, the 3 here, A8 and A9 high, means I'll be grounding the rightmost display, or as I call it here, the ones place. So, and also as a switch, we have a switch for the hexadecimals and for the 2's complement, and they both should be in the low position for this unsigned integers unsigned integers. And for the ones place, how we will program it is that we'll have a loop here from 0 to 255, and we'll write on the address starting on 768, which is what corresponds here to address A8 and A9 high, it will go from 768 to 1023. And as a value that we'll encode, we will take the value that we're counting and take the remainder of the division by 10. And that's what will be written on the ones place. For example, if we have 127, if we divide by 10, we'll have 12 with the remainder of 7. And that's what we want to program on this place. And similarly, for the tens place, or the next display, the way it's wired, it means the selector, the multiplex selector, will be with A8 low and A9 high, which means an address range from 512 to 767. And as a value, we'll first divide this 0 to 255 value by 10, and then take the remainder of the division by 10 to get the tens place. For example, the same 127 divided by 10 in integer is 12, and then the remainder of the division by 10 is 2, so we'll program a 2 on the tens place. And the same goes for the hundreds place. Again, changing the address range given by the counter, and we will then divide the value by 100 this time, and then take the remainder of the division by 10. So the same 127 divided by 100 is a 1, and the remainder of the division of the 1 divided by 10 is a 0, is the 1 division divided by 10 is 0, the remainder is 1, so we program a 1 on the hundreds place. So all seems to be working fine. For the last digit, and since we are programming the unsigned integer sign, we will just program all zeros. For the choose complement, it's the same logic here, but we'll be counting from minus 128 to 127. And of course the address range is different because we have now a select switch here high. But the logic is the same. We'll just take this time the absolute value. We will disregard the minus sign here from the loop, because of course we just want to program a digit on the ones place. We take the absolute value and then the remainder of the division by 10. For the tens place, the same as before, and hundreds place also. But this time, on the signs place, on the leftmost digit, we will program the minus sign for the addresses that we program that goes from minus 128 to minus 1. And after that, from 0 to plus 127, we program zeros. And again, we more or less repeat this pattern for the hexadecimal representation. And for the unsigned hexadecimal, we just take divisions and remainders of 16. And then we'll get the same result as before. And this time, of course, the last two displays will be always representing zeros. And for the choose complement hexadecimals, it follows the same logic. And for the sign, if we are dealing with negative numbers in hexadecimal choose complement, we will just write FF to the leftmost displays. Else, if it's positive, we will write zeros. Well, that's it for the digits. And now what we have here is a simple setup function to set up our serial, to prompt us to press Y to continue with programming, so that we won't immediately start programming whatever is in the Arduino's memory as soon as we power it on. And well, if we select Y, then we'll do the programming tasks that we selected on the beginning. And for this part here, let's just firstly erase the EEPROM just and dump the contents just to make sure it is blank. So we come here, we comment out the digits, and then we just transfer this to the Arduino. Okay, about to program the ROM, press Y, and then press Y, it will erase the EEPROM. I'll speed up the video here a little bit so it won't be too boring. Okay, then as we have seen, our dump here is consists of all ones, so the EEPROM is really blank, and we can then finally program the digits to comment out the erase and then let the program do its thing. And we're done. As we can see here, half of the EEPROM is left blank as expected, but the other half is filled with data. So we're now finally ready then to test our decoder. We just have to release the EEPROM here from its socket finally, and then plug it in the decoder and test it out. And as you can see, it's working pretty well. The display is decoding the counter, is counting up from 0 to 255. And I'm actually not using the counter we built yet, because it's a little cumbersome to connect things in this perf board without making a permanent connection. So I just use the EEPROM programmer to output a simple code that will count. And so we can see that the display is working pretty well. And also I have programmed the to complement with the push of this button. And if we push here, you will see that as it comes to the 127, it will jump to minus 128, which is what we would expect to a binary encoded as a to complement number. And it's almost there, and we'll see that by 127 it should jump to minus 128. Yeah, that's it. Now it's counting towards 0 as it would from 255.